All right, thank you everyone for being here for this edition of the 1W-MINDS seminar. Today our speaker is Qing Chu, who's in the Electrical Engineering and Computer Science Department at the University of Michigan. Qing was recently awarded an NSF Career Award and also an Amazon Research Award. And today he's going to talk to us about the emergence of generalizability and semantic low-dimensional subspaces and diffusion models. So go ahead, take it away. Thank you for being here.
Okay. Yeah, thanks for Christian for the great introduction. So today I want to talk about something I mean, I have been working on diffusion models for around 2 years, or 1/2 to 2 years. And today I want to show you something I find quite interesting in the generalization and the controllability of diffusion models. I think this is a very different from the classical like supervised learning setting. And I think in generative models, right, one of the most important thing is that how can we distinguish between memorization or generalization instead of purely evaluating the model performance based on the generation quality. And this is something I want to talk about, and also how to explore the intrinsic dimension in the data to understand generalization, how to use this kind of intrinsic structure of data to enable controllability of this kind of generative AI models. So without further ado, I want to get started and give you a broader picture first about this diffusion type of generative AI models. Um, and then in the past a decade, like 12 to 15 years, right, we have witnessed this explosive growth of generative AI, especially in the last 5 years. And this idea of a generative model is starting from this variational autoencoder, which is around like introduced in 2013. And later on, right, we have generative models for languages from this transformer to the BERT to ChatGPT, right? And now we have GPT 3 to 4. And for a video or image generation, and this started from this variational autoencoder to GAN to clip models, and recently this diffusion models takes off, right? From this stable diffusion from Stability AI to imaging, DALI, and from OpenAI, and very recently, I think early this year, OpenAI had released this kind of so-called Sora model, right? They can generate videos using enabled by diffusion models. So what is generative AI models? Basically the idea here is that you want to train a machine learning model uh, on different type of modalities, say images, audio, text, etc., right? But you don't have any label, right? You just want to train the model on this input data. And once the model you trained, right, you input the model some pure noise, and your hope is that the model can generate something that semantically meaningful, right? You want to say you input some images and you hope that you input some noise, the model can generate something realistic. But these are different from training data, right? You don't want your model to just to memorize your training data, but you want your model to generate something like realistic that is different from the training data, and hopeful you can manipulate the generation, right? You can control what you want to generate from those models. And the idea of generative model is start from this variational autoencoder, right? So the variational autoencoder basically originally people are designing autoencoders for uh, i- image compression or feature extraction, right? So you are and essentially you are focusing on the encoder part. You want to use the encoder to encode your image to a latent space that you can extract representations or do compression. And the decoder is basically a byproduct of this kind of autoencoder loss design. But later on, people find that actually you can use decoder to do generation, right? You input some noise, and the decoder can generate like images or other type of content. But unfortunately, because you are doing representation learning and generative modeling at the same time, often the generation quality of variational autoencoder is not so good. And in 2014, people introduced this idea called generative adversarial network, right? They are training a generator and discriminator at the same time, and the generator is, and the original goal is like you want to learn a discriminator to discriminate between real images and fake images, and then as a byproduct, the generator can generate some photorealistic images, right? But unfortunately, again, suffered this issue of mode collapse, right? So because the loss function you designed is a minimax object function, that solving a minimax problem actually is not very stable, that you can encounter this kind of mode collapse issues that it works pretty well on small scale data set, but once you scale up your data set to training those kind of generative models, the GAN suffers mode collapse, and it's very hard to deal with this when you scale up your models. And recently, right, this field of generative model has been taken over by diffusion models. So one of the difference that you just notice is that the diffusion models, compared to GAN and VE type of models, GAN and VE models, they are doing one-step generation. So you are starting from a pure noise, you input the noise into the network, and you are one step, you will be generating something. But the diffusion model is doing something different. So you are starting from a pure noise, and you are gradually removing the noise using a neural network until you generate something meaningful, right? Uh, and and diffusion model also has some benefit of controllability, that you can enable all different kind of controls of the generation process. For example, in stable diffusion, right? You can use this text to image guidance that you input a text prompt, and you can control the content you want to generate using this kind of a diffusion type of generative models. And you can also use gradient guidance in the sampling process, where you can use this kind of a gradient guidance to solve all kinds of image uh, reconstruction problem, restoration problems like imprinting, deblurring, super illusion, and phase retrieval, this kind of nonlinear image restoration problems. And moreover, you can also control the neuron, the generation using some sketch. And this is a work called ControlNet that was the SCCV best paper last year. And essentially, what they are doing is that you can input some sketch, right? You can just find like sketch some images, and you give a text prompt into the neural network, and the neural network will, based on your sketch, they can generate something like at your demand, right? So there's all kinds of ways to control those models, and that's why also people like diffusion models. And more recently, that by OpenAI, right? Early this year, they released this so-called Sora model that you can generate videos from uh, using these diffusion models, right? So this enables a lot of different kind of generation modalities, and you can generate like pretty meaningful content using diffusion models. And also diffusion models is good because the training loss actually is very simple, which we'll see later, is that you don't suffer much from this mode collapse issues, that you can scale up your model significantly without suffering from this mode collapse. So what exactly is diffusion models? Actually, diffusion models has two process. So it involves of a forward diffusion process, which is a relatively trivial process. Well, the more important process is the reverse sampling process, where you want to generate an image from a pure noise. And the forward process is pretty straightforward. Is that you're starting from pure image, say X naught, you are injecting gradually injecting noise into your image. And if you take in the injection step too many times, then it will be becoming pure noise at the XT T step, right? And this is a relatively trivial process, right? It's just you are gradually injecting noise to the image, and until it reaches approximately a Gaussian like noise, white noise. And this forward process can be, if you continue, and this is a discrete word, right? But if you uh, consider reducing the time steps to a limit, then you can describe this as a forward stochastic differential equation. So here, this function f and g, they are all noise scheduling functions that they are predefined or pre-given. And this W is a Brownian motion. This is a Gaussian noise you are injecting to the process. Um, and this is something that's not quite relative straightforward. But the most important thing is that actually this forward process can be reversed. And this is some work by applied mathematician in the late 80s, and recently by Yang Song's group from Stanford. They show that this reverse forward process actually can be reversed using a probability flow ODE uh, that you can reverse this process, this forward process, from a Gaussian noise back to the clean image, uh, characterized by this uh, ODE equation, right? Where this f and g is the same with this forward process. But the thing is that if you want to reverse this process, you need to know the score functions, where it's the gradient of the log of the distribution at time step t, right? And if you can know the score function, the stand score function, where you take the derivative with respect to x, if you know the score function, then actually you can reverse this process back to the clean image. And however, in practice, right, you don't even know the underlying distribution of your data, right? So your data is drawn from image distribution, and you don't know the underlying distribution of your data. And when you're injecting the noise at each different time steps, you don't know the distribution PT here, right? So this whole reversal is depending that you know the score function here, but you don't know the score function in practice. So you cannot just directly apply this process, this reverse process, right? And how can we do this? Well, remember, neural networks are universal approximators, right? So the idea here is that if we want to use this diffusion model to generate images, then the idea is that let's use a neural network to approximate the score functions here, right? And from the early works of diffusion models, right, the people are using this so-called UNet to approximate the score function, right? You have a time where T is denoting the time embedding or the noise levels, right? You are controlling the denoising level by giving a time step embedding into the neural network. And you can control the neural network through weight sharing for different score functions at different time steps. And later on, uh, later 2 years ago, people introduced this transformer-based models to approximate the score functions, and they find that they can achieving comparable, yeah, even better generation results using transformers. I think one another two reasons that people like transformers versus UNet-based models is that transformers better satisfy the scaling law, right? So there's an empirical scaling law behind transformers, such that their performance is more predictable based on the model size and the training data set. Another reason is because you can use cross-attention in transformers to enable multimodal learning, like how more better control using tags to control the generation through this cross-attention in transformers. So that's why people like transformers more nowadays. So if you look at DALL-E 3 and stable diffusion 3, They are all based on transformer models nowadays. So this is good. So we know that if we want to do the generation, we can use a neural network to approximate the score, right? But the remaining question is that how can we train the neural network uh, to approximate the score, right? And the idea is pretty simple. So if you want to do this, you just do this score matching, right? You just minimize the distance between the optimal score versus your neural network, where as theta is your neural network you want to learn, and theta the parameters. Uh, but the thing is, directly minimizing loss actually is not very straightforward because you don't know the underlying score function of every time step, right? How can you minimize this if you don't know this term here? Well, there's a Tweedy's formula, right? Actually, through using Tweedy's formula for Gaussian distributions, actually, you can show that minimizing this population loss actually is equivalent to minimizing a loss like this, where epsilon is a pure Gaussian noise, and basically your network is just predicting the noise at different noise levels, right? So this is something that actually you can minimize, right? You can run stochastic gradient method where you can empirically draw a batch of samples, draw the noise, and draw the images from the data distribution, and then you can run stochastic gradient to minimize the loss function. Uh, However, but the thing is that people find that diffusion models work very well in practice, but there are many questions that hasn't been well addressed or answered theoretically, and actually neither. So one of the questions that we are very interested about is generalization, right? So the question is, uh, well, the diffusion models are trained on finite number of training samples, right? They are trained on just on a finite number of training data points. Why you train a model on finite samples, you can generate new samples, right? Why your model doesn't memorize, but you can generate new samples by training your model on a finite number of training data points. That's something that quite puzzling. Another question is that how can you control your model, right? How can you manipulate your generation process? Well, people might say that we can use text to image to control the generation, which works pretty well. But the question is that the text to image guidance cannot do precise control, right? You want to manipulate your image generation, how to do precise uh, control and how to do this disentangled attribute manipulation is something that not very straightforward for diffusion models that we want to address in this talk. So the key theme of this talk, what I want to show you is that how can we better understand the generalization? How can we distinguish between memorization and generalization in diffusion models? And how can we understand why tuning of finite samples we can enable generalization? And actually, this is embedded on the intrinsic structures in the data, that there's a lot of low dimension structures in your data that can enable generalization of your diffusion models. And also, we'll leverage this to control the generalization of diffusion models. And this is something that we want to elaborate in this talk. But before I talk about generalization and the control of diffusion models, I want to first introduce an intriguing phenomenon that strongly correlates with generalization, which is called reproducibility phenomena in diffusion models that I want to talk about first. Um, so first, I want to start with a question about diffusion models regarding to this phenomenon. That so here the setup is the following. So you have two diffusion models. Say as theta one is denoting one diffusion model. For example, as theta one is a UNet-based diffusion model, and as theta two is another diffusion model, which is parameterized by say a transformer. And you are training those two models. on the same data set. You are training on the same data set with sufficient number of samples. And once both model are trained, you will be start sampling from the same noise, right? You give the same noise to the two different diffusion models, and you are also using the same ODE sampler to do the sampling process. And then you generate two images, like image one and image two, right? The image one is generated from S theta one, and image two is generated from S theta two. So my question is, uh, what's the relationship between image one and image two, or do they have any relationship here? Um, any guess from the audience? Yes, just feel free.
I think they're really very close to each other.
Yes, exactly. That's why we call this phenomenon reproducibility, right? So, um, so the answer is actually the generated images from the same noise, even you are using different models, they will be generating something very similar to each other. And this is a result that we showed in our SML paper, where um, we used a different type of models. So this DDAPM is using UNet, and this UVIT is using a transformer-based models. And this saying in the middle is consistent training, right? You are using different type of laws to train your diffusion models. And here we are training under different scenarios, and the figure I'm showing here is that if you look at the same index here, actually we are starting from the same noise, right? This one, and this one, they are starting from the same noise, and this one, they are using the same noise, right? And if you compare the similarity visually, you can see that actually the models actually are generating something very similar to each other, right? Even they are trained uh, through different procedures. They are generating very similar contents to each other. And that's why we call this is a reproducibility phenomenon in diffusion models, that you're starting from the same noise, you're generating something actually pretty close to each other, regardless of training procedure, the network architecture, etc. Uh, and this is just a visual, uh, like a demonstration, right? Can we quantify whether the similarity, I mean, quantify the similarity between different models? And actually, we can do this. That is why we introduce a quantitative measure to measure the similarity. And the way we measure the reproducibility between two models is, say if we have two models, right? They generate two images, like x1, x2 are two images. And we measure the similarity of the two images in the latent space of a self-supervised learner network, right? We're using a self-supervised learning to learn a network, and then we use a network to map the images into the embedding space. And then when we compare the similarity in the embedding space to measure whether the two images are similar to each other, and the reason we use a neural network to do this kind of projection to the embedding space is because we want to get rid of some scaling color scaling differences, right? We want to that's why we are using introduce this cosine similarity in the embedding space of a neural network. And then we can define uh, introduce the definition of reproducibility score. So the reproducibility score is based on this cosine similarity metric, where the metrics we call MSCD metric, right? So here we are setting a pretty high threshold. So once the threshold, the similarity is larger than certain threshold, uh, and then we say that there's a reproducibility. And we are trying to use a, yes, any question?
Sorry, this is just a quick question, but the self-supervised model, I assume that's just trained independently of these two diffusion models, likely on the same sort of data set?
Yes, exactly. Actually, you can use, I mean, we find that actually you can use this kind of self-copy detection type of training. This is a SAOPR work that they do this kind of self-copy detection by training a self-supervised learning network. And you can also use some like open source network like Dino, like from Facebook, that yeah, it works even better.
Okay, makes sense.
Yeah.
Yeah.
Yeah, so the reproducibility score is a probability measure. We define this as a probability measure, and this probability measure is between 0 and 1, right? And the way we measure this probability is by in practice is that we will be drawing like say samples like say 100,000 noise, and then we generate images and we empirically evaluate this probability measure to see whether there's reproducibility between two different models, right? So here, this similarity is defined on individual images, but we use this probability measure to measure the similarity between different models. And this is this is a demonstration of reproducibility by showing the similarity matrix between different models. And these models actually are trained using different architectures, different training losses, sampling procedures, etc. But you can see that even the lowest similarity here is 0.7, right? This probability measure is 0.7, which means that actually there's a pretty high reproducibility between different models. Right. And actually, we can do a more comprehensive study, right? We did a much more comprehensive study and visualize this probability matrix across all different kind of models. And you can see that actually there's a pretty high reproducibility between different models, right? So this suggests that actually diffusion models, this reproducibility actually is a prevalent phenomenon in diffusion models. But however, you compare to other type of generative models like GAN-based or versional autoencoder, they don't have this kind of reproducibility. Like say if you train spectral GAN or WGAN, this is two different type of GAN architectures on the same data set, and you generate images from the same noise, actually there's a zero reproducibility, right? You can see the cross term here is zero, right? It means that there's almost no reproducibility between those models on GAN or VAEs. But this is a prevalent phenomenon in diffusion models. And also, when we are releasing our work last October, there's a concurrent work from Stephen Mallet and Eric Simoseli's group that defines something complementary to what we find here. So here the difference, and this is actually a clear outstanding paper this year, but unfortunately our work get rejected at clear. So yeah. Um, So what they find is that, so here what we did is that we trained the model on the same data set, right? But we are using different model architectures training procedure. What they did is something different, that they train the same model, right? They are using the same model, but they are training the model on non-overlapping data set. So for example, you have an FMHQ data set, and you just draw two subsets. So it's here S1 and S2 are two subsets of the overall data set. And then you train your model on those subsets, right? And this S1, S2, they are non-overlapping to each other. So basically, they don't have any overlapping training samples. And then you will train the same model on these two different data sets. And once the model you trained, you draw from the same noise to generate images. And here is an illustration of a different number of training samples. And you will see some interesting, right? So here, this is a second row is generated from S1, and the third row is generated from S2. And you can see that when the number of training samples is large enough, right, the model is reproducing to each other, but they are different from the training data set, right? But there's no reproducibility when your training data set is small. Actually, we did a more quantitative study on this, right? So this reproducibility is affected by the training data sets and the model capacity here, right? And that's why we did a more comprehensive study in our work. And here, what we did is that we are training the model and comparing the reproducibility between different models on a CIFAR data set. So here, the x-axis here is the size of your training data, and the y-axis here is the reproducibility between different models. And what you can see that actually this reproducibility is not always large, right? So it's only that when in two regimes, the reproducibility is large. One I call the memorization regime, where when you have small training data set, uh, you have reproducibility between different models. And then when you increase your data set, the reproducibility diminishes. And until you reach a certain point, there's a sharp transition, right? You again, the reproducibility re-emerges, right? And it's something quite interesting. And actually, this reproducibility phenomenon strongly correlates with generalizability, where whether your diffusion model generates samples, and that's why we want to also plot how diffusion model generates samples. So here we measure the generalization of diffusion models as follows. So we call a diffusion model is generalizing is that if you can generate a sample, so sample X is a sample drawn from a diffusion model, generated from diffusion model. And then we compare the generated sample with all the training data set. So if the sample is very different from any of the points in the training sample, then we say that we are generalizing, and this generalization score will be 1. So if X is close to 1, any one of the samples, then we say this is memorizing because it's basically reproducing one of the samples in your training data set, right? And basically the generalization score here is also probably to measure between 0 and 1. When it's close to 0, which means memorization, and when it's closer to 1, it means that you are generating new samples, and this is a generalization. And if you look at those two figures together, right, you can see something quite interesting, is that in the memorization regime, right, you're purely memorizing your training samples, and that's where you have reproducibility. And what I believe is that reproducibility is because you are basically reproducing all the different diffusion models are basically reproducing the same sample in the training data set, right? And that's why you have high reproducibility and you are memorizing, right? And with increasing your training data set, there's a co-emergence of generalization and the reproducibility, which means that the diffusion model actually are learning something else. They are not trying to memorize the training data set anymore. They're trying to learn the underlying distribution of your data. And they're all learning the same underlying distribution of your data. And that's why they have reproducibility and also generalization of your diffusion models. And basically, there's two distinct regimes based on the training data set and model capacity that affects the generalization and memorization. And this also occurs in representation learning. Actually, diffusion models recently, people find that they can also use this as a representation learner. That if you have limited samples, right, you're memorizing the training sample, you don't have general representation ability. That only you have large enough samples, you can generalize, and you gain representation power of diffusion models as well. So this is interesting in terms of this reproducibility phenomenon that actually it shed light of generalization. But the question is that how can we mathematically understand the generalization of diffusion models? This is something that I want to talk about next. So the reproducibility, if you look at the ODE sampler, right, the reproducibility basically is saying that if you're starting from the same noise, they all generate the same image, then which means that you're basically learning the same score functions, right? If you're learning the same score function, then you have reproducibility using the same ODE sampler. And reproducibility basically means that the diffusion models can learn all learn the same score function. But the lingering question is that what kind of distribution the score function, I mean, what kind of distribution the diffusion model is learning? But obviously, if you look at this figure, right, it's memorization to generalization, which means that when your training data size changes, the diffusion model actually are learning different distributions, right? And when you have limited samples, you can think that diffusion model basically is learning the empirical distribution, right? And that's why the diffusion is purely memorizing, right? And the empirical distribution can be described by this multi-delta distribution, where yi is a training samples, and this empirical distribution, basically a summation of multiple delta at your training data points, that in the memorization regime, your diffusion model is basically learning the score function of this multi-delta distribution, right? This multi-delta distribution can be visualized as follows. And you can imagine, right? So from memorization to generalization, when you're increasing your number of samples, maybe the generalization is because the interpolation of the underlying distribution by the empirical distribution, right? So you can imagine when you're increasing the number of samples, where your n is the number of samples, gets to very large, then your empirical distribution will be approximating your underlying distribution, right? But the question here is that for your empirical distribution to well approximate or epsilon close approximate your underlying distribution, you might run into the curse of dimensionality. I mean, for image dataset, right? So in the worst case, you can show that for arbitrary distribution, that the number of samples you need to approximate the underlying distribution, the arbitrary distribution is growing exponentially with respect to dimension, right? Which means that you need exponential many samples to approximate the underlying distribution. It doesn't seem to be very reasonable. But if you look at the generalization in diffusion models on CIFAR data or image dataset, the number of samples you need actually is much less. And this is a visualization, show that the number of samples you need is around 10,000, which much less than the worst case scenario, right? Which means that the diffusion model can learn the underlying distribution without the curse of dimensionality, right? And this doesn't seem to be, clear why this happens. So I think the reason why diffusion model can learn the underlying distribution without the curse dimensionality is because your intrinsic dimension of your data distribution is low. And actually, this can be showed by the experiment on the image data, that we try to measure the intrinsic dimension in the models. And here, what we are doing here, I'm showing here, is that here we are considering a different formulation of diffusion models, that we are considering this denoising autoencoder, that we are learning a neural network to directly predict the image, minimizing a variant of this score matching loss. And this can be because it's almost equivalent because the tweet is formula I'm showing here. And here, this plot I'm showing here is that we are trying to calculate the Jacobian of at xt of this kind of denoising autoencoder, and we are showing you. I'm showing here is across all the time steps of the rank, the numerical rank of the Jacobian, right? And you can show that actually this Jacobian, you can show a rank curve like this. So here, what I'm showing, the x is the number of noise levels, and the y-axis is a ratio between the numerical rank and the ambient dimension. And you can see that actually the rank, actually at a certain point, it's very low, right? Here is plotting the log scale, right? But you can see that actually the intrinsic rank of this Jacobian is around 10 to the minus 2, right? Which is very low, which means that actually the Jacobian is very low rank. And actually this low rankness in your model is reflecting the low rankness in your data as well. So actually, if you try to measure the intrinsic dimension of your data, even on ImageNet dataset, people there's a clear paper, right? They measure the intrinsic dimension. Actually, the intrinsic dimension, even on ImageNet, is around 34 to 35 or something. Sorry, 40, 43, 45, something. And if you look at all the other type of classical image data set, actually the intrinsic dimension is ranging from 10 to 30. So which means that actually there's a lot of benign intrinsic low dimensionality in your data, that there's a blessing of dimensionality in the data that it can enable a diffusion model to learn the underlying distribution, right? This kind of benign distributions with finite number of samples that skew with intrinsic dimension rather than the ambient dimension of your data, right? But however, there's another challenge is that if you really want to mathematically understand the distribution learning, the image distribution is very complicated, right? You don't know how to describe the image distribution. And to start a distribution learning, maybe a good idea is to start with something simple that can capture this kind of intrinsic low dimensionality in your image data set. And that's why we start this so-called mixture low-rank Gaussian distribution to characterize, to see how our diffusion model can approximate such a distribution, right? And here is a mixture low-rank Gaussian is essentially a union of subspace model, right? So here we have a bunch of subspaces where they are orthogonal to each other, where this UI is basically the basis of each subspace. And you can imagine for each subspace, the data is generated following Gaussian distribution restricted to the subspace, right? And here we are considering whether diffusion model can learn this kind of mixture low-rank Gaussian distribution and how many samples we need to learn such a mixture low-rank Gaussian distributions. And the nice thing of this mixture low-rank Gaussian is because each subspace actually is a low dimension, right? It's just a low dimensional subspace. And also for Gaussians, right, we can mathematically characterize its score function on this posterior mean estimator, right? And this all can be analytically derived for this so-called mixture low-rank Gaussian distribution. And this is the lemma shows you how this posterior mean estimator looks like for this specific low-rank Gaussian. And if you look at this, right, actually this loss function, I mean, this is pretty have a nice closed form here, right? And if we want to use a DAE formulation to solve the problem, right, the DAE formulation is basically approximating this posterior mean estimator. And if you look at this closed form, where the idea here whether is that maybe we can parameterize our network close to this DAE. And here, as a starting point, we consider there's only a single low-rank Gaussian where you just consider K, the number of clusters is equal to 1. And in that case, we parameterize our neural network like this, right? And if you consider a score function, actually this is pretty close to the UNet with the skip connection. And when you parameterize your neural network like this, what's surprising thing you can show is that the training loss actually can be reduced to a principal component analysis problem, right? Actually, the DAE training loss actually essentially equal to the PCA problem, right? And we know that for PCA problem, the number of samples to learn the basis actually scales with the intrinsic dimension, right? If your number of training samples is larger than the intrinsic dimension, you can learn the basis. If your number of samples is smaller, then you cannot learn the basis. And this characterizes this kind of phase transition from not learning the basis to learning the basis. And this idea can be generalized to multiple subspaces, right? If your number of subspaces larger than 1, you can correspondingly parameterize your neural network like this, where you only minimize the basis for the parameterization. And you can show the problem actually is equivalent to subspace clustering, right? And we also know that subspace clustering, there's a phase transition depending whether you have enough samples for each subspace, right? And experimentally, we can show such a phase transition, right? This is the comparison between training for solving PCA and diffusion models, right? There's a sharp phase transition depending on the number of samples you have. And for subspace clustering and diffusion models, you can show a similar phase transition here, right? And this is only for verification of our theory for the specific model. But this phase transition actually do exist in practical neural networks. And this is a visualization of the phase transition from memorization to generalization, that you are learning a fixed capacity unit on real image dataset, and on this mixture low rank Gaussian, you can see that there's a phase transition from memorization to generalization, right? Depending on the number of samples you have. Moreover, what another thing we find is that actually the basis of the Jacobian, the use, actually each column of the basis has semantic meanings that you can manipulate your generation. So here is a showing that if you manipulate your basis along, manipulate generation along each of the bases, actually you can uh, control the generation by controlling only one attribute of the content, right? You can control the gender, the head, the figure, the color, and the hair. You don't uh, like change other attributes in your data, right? But if you're using arbitrary direction, you will change the images. So I think I only have a few minutes left, so I will just shed a little more light of give you some insights, intuitions, how we can enable disentangle generation or controllability of diffusion models. Uh, Follow this idea, this result I'm showing here. So this is another work that we published in NIPS this year, that we exploring this kind of low dimensional structures in your diffusion models, that we can enable control generation that we of your diffusion models in a learning free manner. And we call this method low rank controllable image generation, or local edit of method. So we can, based on this understanding of generalization, actually we can enable disentangled, localized, and precise editing of your images. And this is some result I show you here, right? We can use some directions to add your mouth shape, hair curvature, hair amount, eye shape, etc. And also we find that the editing direction we find actually can be transferable. For example, if you find the editing direction on one of the face images, actually you can transfer the editing direction to another image. And this is also transferred, can be transferred across different noise levels, right? If you find this kind of an editing in at time step 0.5, you can also transfer this to a different time step. Another thing we find this editing direction interesting is that they are disentangled and they can be composed together. For example, if you find an editing direction that can change the eye size, and you find another direction can changing the smile of your image, and really you can compose them together, and they will be editing different attribute of the image without distorting the other part of the image, right? You can see that you can edit your image, your eye, and the smile at the same time, and the editing direction can be composed together. And moreover, this editing direction actually pretty linear, right? If you linearly change the strength of the editing direction, actually you can change this mouse open to close, right? By changing the editing strength of the method. And we can also enable text to image editing that say adding a glass or changing the mask, etc. So this is some results that I'm describing here, but the question is that how can we achieve this? And the idea to achieve this is embedded in the posterior mean estimator of using diffusion models, right? So let's use f theta to denote this posterior mean estimator which is a mapping from xt to x0. And what we find actually this posterior mean estimator actually have very nice properties. So one of the nice property is that this posterior mean estimator actually is very linear. So if you do a linear approximate a Taylor expansion, right, first order Taylor expansion at xt, and you can find that actually this L theta actually well approximates your f theta for most of the the time steps. And the Jacobian, actually the Jacobian is pretty low rank as well. So this is a demonstration, right? This is the left figure is showing you the low rankness of the Jacobian, and you can show that actually the Jacobian is pretty low rank in the middle time steps. And the figure on the right is measuring the similarity between the f theta and the L theta, right? You just measure the similarity across different strings, and you can see that actually there's a very high similarity using different metrics, right? Even for very large lambda, at the time step t equal to 0.7, and you can see that the L theta, the first order Taylor expansion, well approximates the posterior mean estimator, right? And based on the empirical observed linearity, can enable the editing of the control of your diffusion models. And what we do to control is that let's do a singular value decomposition of the Jacobian, right? And we know the Jacobian is pretty low rank when t is around 0.7 or 0.6, for example. And then we can just do a compact singular value decomposition of this matrix. And when we're editing the image, we'll use delta x. Well, delta x, we will be using one of the singular vectors in the Jacobian, right? And if you use a singular vector, you hit the delta x with this Jacobian by orthogonality, right? We'll cancel out most of the directions, where you are only leaving a direction of a ui, where ui is a basis of your Jacobian, right? A singular vector of the Jacobian. And this singular vector has semantic meanings. And that's how we can make edit of your images, right? And another reason is because the posterior mean estimator is pretty linear, right? And that's why this kind of linearity enables that we can do this kind of linear change of the directions. And that's basically the idea, right? There's a more complicated stuff, technical stuff involved, but essentially this is a basic idea that how can we enable this kind of learning-free distangled edit of your image using diffusion models. And this is the visualization of the editing directions you find, right? You can see that they're corresponding to eyes, lips, eyebrows, brows, nose, etc., right? And we're also comparing our method with all existing methods that are pretty heuristic, where you can see that we are trying to add a red lipstick to the image, right? And our method actually is more natural compared to other methods. And if you look at other methods, they will globally distort the image, but our methods only adds a red lipstick to the face. Right. I think I have maybe a little bit time left. There's another work that we are currently under submission that other than editing your image, actually you can also use this idea, this low-rank Jacobian to do watermarking, right? To do watermarking of your diffusion models. And so the existing method to do watermarking of diffusion models is that they will be injecting watermark like in the frequency domain of your original noise, right? Remember, your diffusion model is starting from pure noise to generate image. And if you want to inject a watermark, what they do is that they will be doing a Fourier transform of your noise. And then they will, in the low frequency band, they will inject a watermark in the noise here. But this will significantly distort your original image, right? If you look at the figures in the middle of the existing approach. And the reason for this is because if you look at this rank curve, right? So the Jacobian is full rank, right? If you inject the noise, the watermark in the Jacobian, which is full rank, you of course distort the image. But what if you inject in the null space at a intermediate time step, right? So if you look at the intermediate time step, the Jacobian is very low rank. If you inject your watermark in the Jacobian, in the null space of the Jacobian, there will be less distortion of your image. And this is the basic idea that we propose for watermarking diffusion models is that instead of injecting the watermark in the original noise space, we will be injecting the watermark in the intermediate steps of your diffusion process, right? And especially we'll inject the watermark in the null space of the Jacobian, then it will lead to less distortion of your images. And this is how we do this, right? If you look at the image that we generated with watermark, right, they are almost the same with original image. And also the methods we did is more robust. It's easy to detect and with less distortions of the images. So finally, I want to conclude here. So in this talk, I showed you there's some interesting phenomena in diffusion models in terms of generalizability and controllability, and everything is strongly due to the intrinsic structures in your data as well as your models, right? By understanding this kind of reproducibility, this memorization to generalization, right, and how diffusion models are able to learn the low-dimensional distributions that it involves that to understand how can we control the diffusion models for better generalization. I think although we did some early studying of generalization, but I think there's a lot of room to, lots of open questions to be further explored, right? How can we study the generalization to memorization beyond the simple parameterization of our neural network, right? And it also opens more questions, right? If you know the Jacobian is low rank, how can we enable more efficient training, more efficient sampling, and better control and interpretation of our diffusion models? How to guarantee safety, privacy, and robustness of our diffusion model is something that worth further exploration. And this is all the work I've showed in this talk. And the first work is a SML work that was the Best Paper Awards in Diffusion Model Workshop last year. And the local edit methods published in NIPS this year. And there are some ongoing submissions of other works. And finally, I want to thank all my collaborators. I welcome any questions. Thank you.